Good morning and welcome to Beyond the Gates, the Collaborative Impact. We are on season 4 this morning and we're going to be talking about smarter bots, safer dams. I am with Taylor Rycroft. He's a research environmental engineer with ERDC Environmental Laboratory, otherwise known as EL. Good morning, Taylor.
Good morning, Annette.
How are you this morning?
I am great. Thanks for asking. How are you doing?
I'm doing great. It's a beautiful day, and we're going to dive into some very important topics this morning. But first of all, let's learn about you. Can you tell me about yourself and your role at ERDC?
Sure. Well, again, my name is Taylor Rycroft. I'm a research environmental engineer at ERDC Environmental Laboratory, and I'm in the environmental risk assessment branch. And I came to ERDC about 8 years ago as a contractor, and I've been a federal employee for about 6 years. And my projects have varied over that time, but most of them come back to the issue of trying to clean something up in the environment. So right now I work on some projects related to invasive species, identifying them underwater and then treating them to eradicate them. I have another project related to sequestering carbon from the ocean using macroalgae. And then there's this project, of course, with the well bot that we're going to get into, and then a couple projects related to harmful algal blooms and trying to clean those up. So my academic background is in bioengineering and then in environmental engineering with a focus on environmental treatment processes. So I've always kind of been interested in cleaning things up, cleaning up water in particular. I'm a certified wastewater operator here in Massachusetts. I actually sit up at the New England district in Boston. So, and then personally, my most defining factor is I have 3 daughters. They're 1 and 3 and 5, and they're my main job and the best part of my life. And they actually bring a lot of inspiration to work. They just like kind of seeing some of the projects that the art stuff they do at school, working with different like slime materials and stuff. We actually used oobleck, which is a little slime they make in preschool, as one of our testing materials to clean with the WellBot early on. So it's just kind of fun. They bring some energy and fun to the workplace as well. So that's kind of me in a nutshell, Annette.
Well, that's very, very cool. Very cool. So we can start off by, if you could explain what a relief well is for earthen dams and levee systems and why their maintenance is so crucial.
That's a great question. I didn't know the answer to that 2 years ago, but I didn't even know the. Yeah,
you're scaring me. I thought you were going to say I don't know the answer.
No, I do now. I didn't before. I would never have known these things existed, but there are so many of them. There's actually 20,000 of them across the core, across 230 different locations. And what they basically are, it's really ingenious, actually, really simple solution. It's like a giant straw poked into the ground at the base of a dam or a levee, and that straw is perforated, and it's designed to allow water to enter it and then come up to the ground level, to the surface. And the reason that's happening is because the water that's being held back by the levee or the dam is still trying to find its way around that dam or levee, and let's just say it's a dam. It tries to go underneath it, and it does successfully, and it pushes up. It's called uplift pressure, and it pushes up on the dam, and that can cause structural problems like cracks in the foundation, and if it's left to go unmitigated, it can cause structural failure. So what the Corps does is that we drill these wells into the ground and give that water a path of least resistance to find its way out to a spot where we want it to go. Mm-hmm. So why is their maintenance really crucial? Because if those wells get gummed up or fouled up and they stop working, that hydrostatic pressure builds back up again, and it starts to push back up on the hydraulic structure. And again, worst case scenario, I mean, the Corps is not going to let this happen, but it could cause failure of that structure. More likely is it would cause some damage, and that damage would be really expensive to fix. So we try to avoid that by keeping these wells maintained and clean so the water can flow through them more easily.
Right. So what are some of the challenges associated with these relief wells are currently cleaned and maintained?
Right. Well, the main challenge, in my opinion, is safety. There is a cost component too, but to clean these wells, there's kind of 2 traditional methods. One's a physical method. If you can picture, it's like a giant toilet plunger we surge the wells using, and since it's an enormous amount of water pressure that you're pushing up and down in the well, you need a big rig to do it. And anytime you're dealing with heavy machinery and a big rig and parts kind of above your head, 15 feet in the air, it starts to just increase the risk profile of that method and more likelihood to get hurt. And obviously the safety culture at ERDC and USACE is a priority, but you just introduce more opportunities for accidents when you're dealing with such heavy machinery. And it usually takes at least 2 operators of the rig who are well, experienced to operate that method. And then there's the chemical method, which makes a lot of sense as well, which is introducing either acid or bleach into the well. And the acid helps degrade some of the chemical crusts that form on the inside of that well. And the bleach kills any of the microorganisms that are forming a biofilm. But anytime you're dealing with hazardous chemicals like acid or bleach, you have to be so careful not to have any sort of dermal or inhalation exposure with those chemicals. And in that case, you really have to be careful that they don't mix, because those two, when they mix, can form chlorine gas, and it's a big problem. And
Right.
could really hurt somebody or kill them. So that's kind of the main issue, is the safety profile of cleaning these wells. And then on the cost side, it's pretty expensive. It's about $10,000 to clean a well. And again, we have 20,000 of them. So it starts to add up as part of the O&M budget for the Corps.
So it sounds like this is an important problem. How did the idea for WellBot come about, and how does it make a difference?
Well, the idea for the WellBot came really just from studying relief wells. I was brought on to a project, and it involved using bleach in relief wells. And part of the project, too, was to look into what are some of the traditional methods for cleaning these and maintaining them. And as I learned more about those methods, I thought that they seemed particularly hazardous and a little bit outdated, honestly. They've been around for decades. So I thought, especially in today's culture of safety that ERDC and USACE are fostering, I thought there must be a better way to do this. So that's kind of, the WellBot came about with, there's got to be a simpler way of cleaning stuff. I spend a lot of time cleaning the dishes from my kids, so I I brush a lot of stuff. I use a lot of, bleach or soap, and so I do a lot of thinking about cleaning. So I just thought, okay, there's got to be something simpler. So how does the WellBot make a difference? The main difference it makes is it eliminates that need for heavy machinery or hazardous chemicals that we were talking about before. So it dramatically improves the safety profile of cleaning a well. It's also significantly less expensive, about 90% less expensive than current methods, because it only costs less than $5,000 to build a WellBot.
Right.
And then you can use it at multiple wells for multiple years. So I think we're going to talk about probably the field trial we're doing with the WellBot. But at the site that we're doing that, Townsend Dam in Vermont, for example, conventional cleaning of the 9 wells there would cost about $90,000. And then if you're using the WellBot, it only costs about $5,000. So it's a significant cost savings.
Little bit.
Yeah, exactly. Pretty dramatic.
So can you walk us through how WellBot works from deployment to operation and how it differs from the traditional methods?
Yeah, so in its simplest sense, the WellBot is just brushes with a UV light. So the brushes, there's 2 brushes, one on the bottom, then there's the UV light, and then there's the brush on the top. And the brush on the bottom oscillates 1.5 rotations, and then it comes back. The brush on the top stays stationary so nothing gets twisted in the well. And then the UV light is just shining bright. And I can kind of go talking about that in a little bit. But all that part is the only part that goes down in the well. And then that's connected to a reel at the top of the well that raises and lowers it. And you can program the reel how far you want it to go down and how far you want it to come back up. So maybe you want it to go minus 60 feet and then come back up to minus 30 feet and just go back and forth in that range. So you set its range. And then that reel is fastened to a cart, a ruggedized cart that can be rolled around. And on that cart are solar panels and the batteries associated with the solar panels. So the whole apparatus is just kind of on this cart. And when the WellBot is done cleaning its first well, you can pull it back up we'll reel it back up, and then you roll it to the next well. And it doesn't require being plugged in. It's completely off-grid. If you have a grid connection, you can save yourself a lot of hassle with a solar panel and batteries and a lot of weight, and that makes things easier. But it's designed to be used off-grid. And the idea behind it is the brushes work to scrape off the biofilms. That is kind of like a slime that microorganisms form on the sides of the well, and also chemical crusts. So, there's chemicals that oxidize in the well and form these kind of scaly crusts inside. And the brushes scrape that off, suspend it in the water column, and then that UV light hits that material. And if it's a living organism, we have one wavelength coming off the UV light that affects the DNA of the microorganisms and kills them. So it's germicidal UV light is what that's called. And then there's another wavelength from the UV light that forms what's called a reactive oxygen species. And that just reacts basically with dissolved chemicals in the well that would otherwise form a crust. So the light is designed to prevent those chemicals and those microorganisms from reforming the scale or the biofilm. And that's the general idea, but it's made from really simple materials, like a chimney sweeping brush, UV lights that are used to just clean water in like fish ponds, like koi ponds,
Right.
An extension cord reel, a stainless steel cart, and some solar panels. Very simple.
Wow. So what were some of the key challenges you faced in developing WellBot, and how did you overcome them?
Well, the main one, and it wasn't that significant. We've had good fortune on this project where there weren't a lot of challenges, which is great. But the main one was figuring out how we were going to attach the reel to a top of a well. And we thought at first that at the top of a well, there's what's called a flange. We thought we would attach the reel to the flange, and that would be great. But then we started to learn more about different well designs and where that flange can be located. Some are underneath a manhole under the ground where you can't fit the reel. Some are 3 feet above the ground. So we decided to make the reel independent of the flange or the well itself and put it on the cart. And actually that was just very good luck, because now the whole apparatus is just on this one movable cart, and the cart houses the batteries and the solar panels, and everything can operate from that. And then you can just roll it up to whatever flange design you encounter, and it works great. So we kind of got lucky on that one. But that was probably our main challenge, was how are we going to actually attach this thing to a well?
Oh, okay. You referenced the field test in Vermont for WellBot. Can you tell us more about that? And what were the most important findings from that test? And how did WellBot perform in real-world conditions?
Yeah, absolutely. So the New England district has been great in hosting us at their Townsend Dam location. And the Townsend Dam, it has 9 relief wells at the base of the dam. And they gave us the opportunity in June to test the WellBot in its first well for 2 weeks out in the environment. And we didn't have funding to do the quantitative testing at that time that we would prefer. So we went with qualitative, which just meant looking at imagery from a down well camera. How did it perform? And we let the WellBot run for 2 weeks out in the open, and it was going up and down in the well, and we took pictures at day 1, day 7, and day 14. And from those pictures, you can really see how effective it is pretty immediately. Within 1 day, it had scraped everything off the side of the well. And at the 7-day picture, everything looks really clean in the water. There's really very little suspended material. It had all settled to the bottom of the well, and the screen looks great. Mm-hmm. And day 14, it looks the same as day 7. So we were hoping that, okay, well, the WellBot really did its job by day 7. We don't need to put it in there for 14 days. That would be ideal. But the big question is, okay, it looks pretty. It looks nice down there now. But did you actually improve the health of the well? And the way to find that out is this quantitative metric called specific capacity. And that's what we use to determine like how healthy a well is. And you want that number to be high. You want the specific capacity to be high, but we can't tell that from imagery. And to get a specific capacity test costs about $5,000 a day. Fortunately, our program manager, Dr. Brandon Boyd, with the Flood and Coastal Systems program, was able to help us get that funding. This FY, within a few months of our first field trial, and put together a much larger field trial with the wells at Townsend Dam to get specific capacity measurements before we treat with the WellBot, and then those specific capacity treatments after, so we can see what kind of impact we have. And so that test is ongoing, and actually we're pulling the WellBot out tomorrow. It's done its final well. We're pulling it out from Townsend Dam tomorrow, and then we're going to do those after measurements of specific capacity. And we have the Savannah District from Savannah, Georgia, helping us with those. They're one of the best rig teams for getting that measurement. So we should have our data within a few weeks to see efficacy-wise, did we get a good specific capacity improvement after 1 day, 7 days, or 21 days. We did 21 days this time. And we also are doing traditional treatment on 2 of the wells to see, okay, how did our WellBot compare to traditional treatment methods? So we're trying to get a better picture of its efficacy that way.
Well, and it also alludes to our theme this year, the collaborative impact, because you can't do it by yourself, right?
No, absolutely, exactly. It's been instrumental having New England District with their knowledge of the wells and the dam, and then Savannah District with their, they have this rig that comes up. It's a tracked vehicle. It's 2 Honda Odysseys. That's the that's the language I speak because that's what I drive. And it's a big rig, and it comes in and it does its measurements. And I can see how that would have a little bit of a negative safety profile working around that thing is pretty big, and that's what they would use too for cleaning the well conventionally. So, right. But then you did ask, how did the WellBot perform in those conditions? And we're really happy with how it performed. We were a little nervous about how's it going to do out here in Vermont weather, which can fluctuate significantly. Like right now, the temps are getting down below freezing overnight, but over the summer it got into the high 90s. So it's done great. It's been outside for I think 11 weeks total since the June field trial, and we had like one small issue, but it was just a silly thing that was easy to fix. But otherwise, it's been really effective, just operating continuously. We're really happy with how it's going. And it's going to be exciting to review the data. I know, I'm nervous. I hope it works. We've talked about it so much. We're so excited about it, and it looks so pretty. I mean, right. If you've seen the pictures, you'll be like, oh, that has to have worked, but right. We don't know. Now, one thing I do want to mention is it's pretty easy to beat conventional treatment because right now, so one district I won't mention, but they said they're spending $10,000 per well to use the acid and bleach method, and they're getting a 3% improvement in specific capacity. Which at that point, you're kind of like, why are we spending that much money to do that? And I don't know. I think we just have to keep trying. Some other places I've read are getting 30% improvement. So right. We're hoping to beat both of those numbers and get a much better improvement in specific capacity, but we'll see. But right now, even the conventional treatments aren't always effective. So. Well, I'm over here going to be pulling for it. So anyway. Thank you. So you had referenced earlier with over 20,000 relief wells in the USACE inventory. How do you see WellBot scaling up to meet the maintenance needs of various districts like you were talking about? Right. No, and just for context, just using nice round numbers, we have 20,000 wells roughly, and they have to be cleaned about every 20 years. And so that's about 1,000 wells per year, let's say. That's roughly we clean them every year. And so we're cleaning, and that at $10,000 per well, we're spending about $10 million per year, and we can get mixed results. I mentioned the 3% improvement, or there's 30%, and I'm sure there's better elsewhere too. But you get mixed results on that $10 million investment. And again, the WellBot costs about $4,000 or $5,000 to build. It can treat multiple wells over many years. So the cost savings is huge. At Townsend Dam alone, that savings, like we said before, was about 90%. So that's the main impact there. And then you mentioned scaling up to all of that. I think the key here, I mean, we could build it. That would be a lot of WellBots to make for 233 locations that we're tracking of levees and dam systems that have these wells. But we filed a patent 13 months ago on the WellBot, and we're hoping that gets approved soon. And then we could license the technology to someone else to mass produce it. Mass produce, absolutely. That's kind of the idea, yeah. And like I said before, too, it's really simple. It's made from mostly off-the-shelf materials, like just brand name stuff that we bought and kind of plugged together.
Mm-hmm.
There are a few custom items, but with CAD drawings these days, you could just give that to someone and they could 3D print it or make it themselves.
That 3D printing thing is so mind-blowing anyway. So
yeah, I don't know that too well, but a lot of folks on my team play with that, and it's incredible the magic they can produce with that.
Absolutely. So I know we've referenced this a little bit, but what are the potential cost savings for districts using WellBot compared to traditional methods, and how does this impact overall dam and levee maintenance budgets?
Yeah, again, back to that number, I guess I sort of prematurely answered that question. But yeah,
I was like, we've talked about that.
$10 million a year across the core. I suppose that's a drop in the bucket for the budget, but if you can save, 90% on that per year, that is a significant savings. And then at the district level, it's pretty remarkable how much, the one district that's getting 3% improvement,
right.
They treated 400 wells over the last 4 years, and that's a big piece of their budget to be treating that many wells and not getting significant results. So hopefully the WellBot, and they said, hey, we're open to ideas. We need something new. And so hopefully this can be that solution for them.
That would be great. Looking ahead, what improvements or enhancements do you envision for WellBot, especially with the potential for remote access and control?
That's the main thing, and that is the main upgrade we want to make is incorporating the ability to control the WellBot remotely. So right now we have no communication with it while it's operating, which is a little nerve-wracking. So we have to, text the folks, the rangers at the Townsend Dam, and just say, hey, go down and check on it, make sure it's still working fine. So we want to invest in being able to remotely access it and not just monitoring whether it's still going, but being able to adjust its up and down speed with the reel, the spin speed of the brushes, and then the depth range. Perhaps we want to change that, and you want to be able to control that from your phone. Other than that, I would say we're really happy with the design. We made some design improvements. I think the main design improvement with the cart initially, I think we said earlier, I hoped to just attach it to the well itself, the flange, but putting it on the cart was a major breakthrough for the design. And overall, it's working great. We just want that remote access.
Awesome. So as we close out today, I'm going to just ask you this one last question. What's the key takeaway you'd like our listeners to have from this conversation?
Okay, the punchline is that the WellBot, yeah, exactly. What I want people to take away is the WellBot is safer and it's cheaper than conventional methods of cleaning a well. And we can use it proactively and preventatively to clean wells regularly instead of reactively cleaning them once they are fouled, like we currently do.
Right.
So that's kind of the thrust of the message.
That sounded like an elevator speech.
You got to say it fast when you're on the elevator, right? So yeah, that's it. That's what I hope sticks in people's heads. That's the plan. And I'll be back with efficacy data when we have that specific capacity data. Fingers crossed that it all works out great.
That's what we need to do is just, maybe next season or the season after that, we'll just have you back on and you can talk about the results of the data and where you go from there.
I look forward to it. Thanks for having me today.
Thank you, Taylor, and have a wonderful day. And thank you, listeners, for listening, and we'll come back at you next week. Have a great day.